Okay, so the topic for this video is going to be isosceles and equilateral triangles, which we've seen in a previous video when we were talking about classifying triangles. But now we're going to be investigating what the properties of them and how to solve problems using them specifically. So last we left off in the last video was we were talking about CPCTC, which was a theorem saying that corresponding parts of congruent triangles were congruent. And what this says is that with the power of CPCTC at his disposal, Euclid, our father of geometry that we're kind of following along with, set out to investigate isosceles triangles. And just as a little recap here with a little additional vocabulary, this says isosceles triangles, an isosceles triangle has two congruent sides called legs and one non-congruent side called a base. So this is just some extra vocabulary here. So if we have our isosceles triangle, the two congruent sides are called legs. So these would be the legs. And then one non-congruent side called a base. So the side that's not equal to the other ones is our base. And the angles adjacent to the base are called base angles. So those two down there are our base angles. And using CPCTC, Euclid proved what he called the base angles theorem. The base angles theorem says if two sides of a triangle are congruent, then the angles opposite them are also congruent. So the way this works is it's saying if you have a triangle with two sides the same, then you also have a triangle with two angles that are the same, which some of you may have seen when we were doing the classifying of triangles video, but I said we would come back to it later on. And so here we are, and we're going to try to prove that that statement is true. So example 1 says, prove that the base angles theorem is true. So this says, if we got AB congruent to BC, so that's our given. We are starting off with this triangle that has two sides that are the same. And we're going to try to prove that angle A and angle C have to be the same as well. Those angles that are opposite these sides. Now, right now, this seems kind of daunting because all the proofs we've been doing have been dealing with proving that two triangles are congruent. And we only have one triangle. So what we're going to do is we're going to make this into two triangles. And this is something that you can do using constructions. Constructions are those set of steps that we can follow to construct, to build things. And one thing that we can do is we can construct a median. So our next step, we're going to draw in median BD. And we can do that using constructions. So our reason over there is going to be a construction. And now what we've got is something much more approachable, right? Sorry, I didn't do my highlighting that I always do. Now let's go back to what we were doing in the previous videos of trying to prove these two triangles to be congruent. Well, we've got BD congruent to BD now, right? That side in the middle, that's the reflexive property. That is an awful X. Let me try that again. So we've got two congruent things. We need a third. Well, we know what a median does, right? A median splits that opposite side in half. So AD must be congruent to CD by definition of median. Okay, that's our three congruent things. And that means that triangle ABD must be congruent to triangle CDE BD by side, side, side. And what do we know about congruent triangles? Well, we know that all of their corresponding parts are also congruent. So angle A must be congruent to angle C by CPCTC. So that is the rationale behind why the base angles theorem is always true. You can always split it into two congruent triangles and prove that the triangles are congruent, and that means that those base angles must be congruent. Okay, so now that we know why it works, let's use it. So example 2 on the inside here says ABC's isosceles, solve for x. Well, if these two sides are the same, that means these two angles opposite them must also be the same. So 7x plus 10 must be equal to 45. Subtract the 10, we get 7x is equal to 35. Divide, and x is 5. Let's check our work as always. If we plug that back in, 7 times 5 is 35, plus 10 is 45. So that looks good to me. What about this one? ABC's isosceles, solve for x and y. Okay, they're getting a little tricky here. Well, those are our legs, right? Those are the sides that are congruent, which means that these two angles opposite them must also be congruent. So x plus 50 must be equal to 3x plus 10. If I subtract the x, I get 2x plus 10 is equal to 50. Subtract the 10, I get 40 is equal to 2x, which means that x is 20. Now, that 2y up at angle C, that's not congruent to the other ones, because that's not the base angles. But let's plug x back in and see what happens. If x is 20, 20 plus 50 is 70. 3 times 20 is 60, plus 10 is 70. So those two angles are the same. That's good. I'm going to put a check because we checked that. And now we got to remember the triangle sum theorem. The triangle sum theorem says that if I add up the 2y, the 70, and the 70, that's got to be equal to 180, right? All three interior angles have to add up to be 180. We proved that in a previous video. So that means 2y plus 140 is equal to 180. That means 2y is equal to 40 if I subtract it. And that actually means that y is 20 also. Interesting. If we plug that back in, 2 times 20 is 40, and 70 plus 40 does equal 180. So check mark for that. That is also true. Okay, next up. It says Euclid also proved that the converse of the base angles theorem is true. Now, we could do that as well. We don't have time to do that in this video, but the converse is also true. It says if two sides of a triangle are congruent, then the angles opposite them are congruent. Oh, I'm sorry. That should be flipped. Yours will be flipped. If two angles are congruent, then the sides opposite them are congruent. And that's what your notes say. That essentially says if this is true, if the base angles are the same, then the sides are the same. Because remember, converse is where we flip things. We flip the hypothesis and conclusion. So that's going to let us solve some questions like this, where if we know that these angles are the same, that means that these sides must be the same. So, for example, we could do 4x plus 6 is equal to 50. Subtract the 6, we get 4x is equal to 44, which means that x is 11. If I plug the 11 back in, 4 times 11 is 44, plus 6 is 50, so that looks good. Now, just be careful, that 60 is a complete distraction. That's the base, right? The base is not the same as the legs. It's the legs that are the same. This one shows us these 22-degree angles being the same. That means that these sides have to be the same. So 9x minus 2 is equal to 5 parentheses x plus 2. 9x minus 2 is equal to, when we distribute, we get 5x plus 10. Subtract the 5x, we get 4x minus 2 is equal to 10. That'll give me 4x is equal to 12, which means that x is 3. Plugging the 3 back in, 3 plus 2 is 5. So 5 times 5 is 25. Over here, 9 times 3 is 27. 27 minus 2 is 25. So that looks good to me. Checked our work, we get a check mark. Okay, so that's isosceles. Let's check out some equilateral stuff. It says, Euclid then moved on to equilateral triangles and proved that the corollary to the base angles theorem is true. So this says, well, just as a recap, an equilateral triangle has 3 congruent sides, right? That's what an equilateral triangle is. All 3 sides are the same. Now, the corollary to the base angles theorem says, if a triangle is equilateral, then it is equiangular. Now, that's kind of interesting. Equiangular is a weird word. But what that means is that if all 3 sides are the same, then all 3 angles are the same. Okay? Corollary just means an addition, so it's just an extension. We already knew that if 2 sides are the same, then 2 angles are the same. Corollary is an addition to that. If 3 sides are the same, then 3 angles are the same. Now, interesting about that, if all 3 angles are the same, and all 3 angles must add up to be 180, then 180 divided by 3 tells us that every equilateral triangle must have 3 angles that are 60 degrees. And once again, some of you guys probably already recognized this when we were dealing with equilateral triangles back in the classifying triangles video. But this is why. It's an extension to the base angles theorem. And we can use this to solve a lot of things. So this one says solve for x, y, and z. Well, I see that all 3 of these sides are the same, meaning this is equilateral. And the corollary to the base angles theorem says that if this thing is equilateral, it's also equiangular, meaning that all 3 of those angles must be the same. And if they're all the same, they're all 60. So that means 10x plus 10 has to be equal to 60. Subtract that 10, we get 50. Divide by 10, and we get x is 5. Plugging that back in, checking our work real fast. 10 times 5 is 50, plus 10 is 60. So I got to check. For the y, that 12y down there, that angle's got to be 60. Divide by 12, and we also get 5, strangely. 12 times 5 is 60, so that works. And then the z, 2z must be equal to 60 as well. Divide by 2, and z is 30. And that also works. So, check, check, check. What's this one say? Solve for x, y, and the perimeter of the triangle. Well, the converse to the corollary of the base angles theorem is also true. Meaning that if all 3 angles are the same, all 3 sides are the same. So this one, we want to find x and y in the perimeter. Well, okay, if all 3 sides are the same, doesn't that mean that all 3 sides are 30? So 8x minus 2 must be equal to 30. Add the 2, I get 32, so x must be 4. 8 times 4 is 32, minus 2 is 30, so that works. And same for the y, right? The 4y plus 2, that's got to be equal to 30 also. Subtract the 2, I get 4y is equal to 28. Divide by 4, and I get 7. 4 times 7 is 28, plus 2 is 30, so that works. And then 30 plus 30 plus 30 is 90. So the perimeter must be 90. Okay. Last one. This is an interesting one. This one's a combination of what looks to be an equilateral triangle and an isosceles triangle. And this one's goofy because we actually have no numbers to start with. But it's only possible if we know our properties, the properties of these different triangles. So one thing right away, if you recognize that this thing is an equilateral triangle, triangle ABC is equilateral. That means that all three of these angles have to be 60, right? And if angle ACD, the big angle, has that box in it, that means that angle is 90 degrees. So 90 minus 30 is 60, meaning that angle BCD, or I'm sorry, not 90 minus 30. I got that backwards. 90 minus the 60 we know leaves us with 30. So that means that angle BCD, this little angle there, that's 30. And then what do we know about isosceles triangles? Well, the base angles theorem says that if the two sides are the same, the two angles are the same. So the other base angle has to be 30. And then finally, if I want to solve for x, I can do the triangle sum theorem. 30 plus x has to be 180. That's 60 plus x equals 180. So x must be 120. Fun little problem there that you can only do if you understand your properties. It looks daunting at first because it's got no numbers, but knowing your properties lets you get there. Okay, so y'all have some problems to try over here on the your turn. You got, I think, 3 isosceles and 3 equilateral problems to try out. Why don't you pause the video, give those a shot, and then come back when you're done and ready to check. Okay, hopefully that went well. This first one, those two sides have to be the same since these two base angles are the same. So 4x plus 3 equals 15. 4x is equal to 12, so x is 3. On this one, converse of the base angles theorem says that if the sides are the same, then the angles are the same. So angle B's got to be the same as angle C. 9x plus 3 has to be equal to 5x plus 35. That's 4x plus 3 is equal to 35. 4x is equal to 32, so x should be 8. This one's kind of interesting. This one, base angles theorem says that if the sides are the same, then the angles are the same. So if angle C is 2x, angle B is also got to be 2x. Now, I'm not going to set 2x equal to 2x. Instead, what I'm going to do is use both of those plus the 88 to do a triangle sum theorem. 2x and 2x is 4x plus 88 is equal to 180. That's 4x is equal to 92, which means that x is 23. All right, over here we got an equilateral triangle. All 3 angles are 60, which means that all 3 sides are the same. So 7x plus 5 has to be equal to 40. 7x is equal to 35, so x is 5. On this one, we've got all 3 sides being the same. They're all 6, which does mean that all 3 angles are 60 because this is equilateral. So 4x just equals 60. Divide by 4, we get 15. And then lastly, we've got to solve for x1 here. We've got all 3 angles being the same, which does mean all 3 sides are the same. Now this one's kind of goofy because you've got 3 different sides that you could set equal to each other. I'm just going to do 3x plus 1 equals x plus 7. But really you could set any 2 of them equal. Subtract the x, you get 2x plus 1 is equal to 7. 2x equals 6, so x is 3. All right, hopefully that went well for you. And that's going to wrap up this video.